Hi there! This noisy contraption sitting next to me is a FANUC, or a FANUC, I'm not sure how you pronounce it, but a PPR, Portable Punch Reader. If you've been watching my channel lately, I've been doing some stuff with vintage computers and punch paper tape. Punch paper tape was one way they would store programs back in the day. You can see some paper tape here sticking out of this thing, little holes in it, 8 holes per row, encoding 8 bits of data. So anyway, my previous video I had something called an AKI teletypesetter keyboard, and that was something that was designed that you would type on it and it would print directly on the tape, and you would take that to use for typesetting, publishing, and I modified that so that I could control it via serial and via Raspberry Pi. While doing that, I realized I need something that I can read these tapes back in with, because it's great to write stuff, but how do you read it? And someone suggested that I look into these FANUC PPRs. And these things are designed for the CNC community, so computer numeric control. Think about people running milling machines, lathes, other machinery that they needed to program from a computer. Now they could type their program in, that was kind of laborious, and the machining environment is probably kind of hostile to magnetic storage devices like discs or magnetic tape, because you've got like lots of magnets and stuff sitting around. So it's not surprising maybe that they settled on paper tape as one possible way to store and load their programs. And that's what this thing was designed for. This is kind of an all-in-one gizmo here. It's got your punch, it's got your reader, and it's got a printer hidden back here that can print a human readable copy. And it's portable, not in the sort of laptop has a battery in it portable sense, but portable in the sense that you can lug it around by its handle, and it's got a cord and you can plug it into the wall, and you can take this over to your machine and you can load your program, stick your program in there and have your milling machine do its thing. I bought one of these because it was recommended to me. It turned out to be a fantastic idea because it's all in one, it does everything you might want to do for reading and writing your punch paper tape on your vintage computers. So what I'm going to do in this video, I'm going to do 3 things. First, I'm going to launch into an immediate demo of this thing so you can see what it does, running from an RC2014, so the popular RC2014 vintage computer, retro computer. And I took on that and I modified the basic interpreter so it has a tape save and a tape load command. So I'll type in my basic program, I'll punch it onto tape, and then we'll read it back in and prove that everything worked. Then I'm going to talk about what I had to do to repair this thing to get it to work. So as you probably noticed from this channel, I buy stuff off eBay. Often it doesn't work, shocking, but often it doesn't work, and I have to fix it. So no surprise here, I fixed this thing. And then third, I'm going to try this out on the Heathkit H8, which is actually sitting back here. Trusty Heathkit H8. I've been doing a lot of videos on that thing lately, but the H8 was designed to work with paper tapes. So, we're going to go in and we'll use that running the actual software that was written and designed for that back in the day to read and write paper tapes from BASIC. So anyway, let's go on a vintage paper tape adventure. Okay, let's jump right into a quick demo. Over here is the RC2014. Next to it is the FANUC PPR, the portable punch reader. Behind it is a monitor. The monitor is hooked up to a Microsoft VGA terminal. The Microsoft VGA terminal, it's a great dumb terminal that lets you turn any VGA monitor and keyboard into a serial terminal. So we've got that hooked up to the RC2014 so we can get a console. Down here is my keyboard, which is slightly out of view. Okay, just to show you a little bit closer what we got set up, this is my original RC2014. The one that came from the UK and I assembled so many years ago, and it's got the original ROM board in it, it's got the original clock board, the original Z80 CPU board, the original RAM board, but I have removed the ACIA serial board and installed an SCC serial board. Now the reason I do that is twofold. First is the SCC has 2 ports instead of the ACIA's 1 port, and for this demo it's going to be important to have both a console and a printer port. And secondly, the SCC has a baud rate generator, so if I want to run my my printer or my punch at 1200 baud, I can easily do that. So I talked about the SCC back when I did the bubble memory video. I talked about it quite a bit in there. I'm not really going to talk about it here. Just know that it is a 2-port serial board that does have the ability to control baud. Now the board that I designed, it has TTL level headers, and I needed to hook up to the punch paper reader. I needed a DB25. So what I have here is just a little DB25 breakout. It's actually repurposed from something else, but it has a DB25 connector, it has a max 202, and a header. So it's just to do the DB25 breakout. And then here we have the connector that goes over to the PPR. Now the other port coming out here is the console. It hooks up to my dumb terminal, which you'll see on the video screen. So let's turn on the RC2014. I will, well, it's already plugged in. Let's just hit the reboot switch. It'll take it a second here to boot up. So we do get a bubble trouble error, and the bubble trouble error is because this is the basic that I wrote for my magnetic bubble memory demo. And it still has some of the bubble memory stuff in there. So there is no bubble board. The bubble board is, you know, if you watch my previous video, it's like a huge board. Don't need it, but I have augmented this basic with some commands for the tape. So if I type in help, we'll actually see more stuff scroll by than you can actually read. But boom, it goes blasting by. You can see I've got down here a T-save and a T-load. Those will go in and out port 1 on the SCC board. So the SCC board being a 2-port serial board, we have 1 port for the console, we have the other port for the tape. So let's type in a simple program. Scott was here. I'm going to type in a couple lines. Mainly because I want to actually get some stuff output on the tape. Print. Let's see, whoops. This is the... So there's our simple little program. You know, we can run it. We could list it. Next, let's save it to tape. So I'm going to turn on the FANUC PPR. Let's advance the tape a little bit. I'll show you how the form feed works. You hit this button. Takes a minute to spin the motor up. That's like our little form feed there. Put it back into normal mode. Now I need to set my my RC2014, my SCC over here. I need to set it to the right baud rate. So I wrote a command in this basic that I've extended called lbaud. And 1200 baud is what I have this thing working at. I want to hit C. I've kind of extended the syntax here. C and I. So the C says that I want to do RTS, CTS flow control. So it's important that this paper tape punch here, it can't run, even at 1200 baud, it can't keep up with 1200 baud. You'll overflow the buffer and not be able to output. So the C turns on flow control, and the I tells it to go in immediate mode rather than waiting for reboot on taking the baud rate setting. So there, we've configured the baud. Now, if I do a T save, it will save it to the tape. We have to turn the punch on first, so that is this button. There we go. And let's hit T save. And let's get some length out of it there. So now we have that program saved to this here paper tape. Now I wrote the save routine, so what I told it to do is to put a little leader here. These are hex 16 bytes. The Heathkit H8 did the same thing on its tape routine, so I just kind of copied that. And then it prints out actually the letters TAPE. That's my signal that yes, this is a tape. And then it spews out the contents of the basic memory. And this will of course be longer based on the program. So let's go ahead and we'll just we'll hit new. That'll erase the program from memory, so it's not there anymore. We take our tape, we'll insert it into the reader over here. Clamp down, so our tape is sitting here. Put it back into remote mode, and then we'll hit T load. And as soon as I push this PTR for paper tape reader button, it's going to suck in this tape and load it into this waiting computer. Now, it was kind of noisy while it did that, and the reason it kind of made that noise, I think, was it was synchronizing that to, you know, the 1200 baud speed, so it was pausing on each line as it read it. But my tload command here succeeded, and if we do a list, there we go, our program is there. And of course we can run it. Now this PPR, it also has a printer in it, and printer's a little bit finicky. Here, let's cancel the tape reader mode. It takes 69 millimeter paper. I couldn't find 69 millimeter paper. It might be the same as 2 3/4 inch cash register paper, which comes out to just about 70 millimeters. That might work. I don't know. But anyway, let's insert the paper into here, and then we will we'll feed it a bit. So we'll hit the printer feed, get it to suck in some paper. Got paper coming out there, and now I need to change the baud rate again. We're going to stick with 1200 baud, but this time I'm going to tell it to use 7-bit because this printer actually expects 7-bit even parity. So my routine, when I tell it to do 7-bit, it'll automatically do the even parity. If you try 8-bit no parity, it isn't going to work right. And then again, we will enable the flow control because this printer does not print at a full 1200 baud, and we will go immediate. So this should work. So what we have to do, put it back in remote mode, and then we'll turn on print. It's ready to go. And then I've got list. Not the fastest thing in the world. Okay, and then I can go over here, I can put it in feed mode, and then let's feed it through the printer. So there, I don't know if you can read that, but it printed out each line of it there. So we've got 10 print. Scott was here. Now it does print a little symbol at the end, which is the line feed. Maybe I can take a picture of this and stick it in the video so people can read it better. But it did actually print, so the printer is working. So this FANUC PPR here, it's a great little unit if you want a paper tape punch, a paper tape reader, and a small cash register style printer. All of your little bits of punched out paper, they show up down here in this little box. Now that we've done a demo, let's talk about what I had to do to get this thing going. Now, I bought this thing off of eBay for 200 bucks. I think that's a pretty good deal. I did do it after learning that a fellow SEBHC user had bought one for $250. And he got lucky. He got a fully functional one for $250 with a couple rolls of paper, a couple rolls of Mylar, and the whole thing just worked. Now that's a really good deal. I bought this one for $200, and not surprisingly, it didn't work. That's just how my luck seems to go on eBay. I did buy it for parts or repair, so you know, not surprising it didn't work. When I got it, there were some screws missing. Always a bad sign with their screws missing. Then I opened it up and I found that wires were disconnected between, you know, the punch and the keypad and the printer and the logic board. If you open up a piece of vintage equipment and find that the connectors are unhooked, that's a really bad sign, because that means somebody else tried to fix it before and they failed. You know, if they'd have succeeded, they'd have hooked all the connectors back up. If they left the connectors unhooked, it probably means, you know, they failed or they were scavenging parts. So I knew this thing was going to be some trouble. Now when you turn this thing on, you turn it on, all of the lights light for about a second. You saw them there, they turned on, then they all went off. I don't know if you could tell that from the video or not, but each one of these has a little LED in it, and there's LEDs above. They all came on about a second or two, then all turned off. Now when I first got this, after I'd wired everything back up, it did not do that. So the lights all stayed on. They just stuck on and the keys wouldn't do anything. You look in the manual and it says logic board failure. Now, fortunately, that's one thing I can do, is I can fix logic boards. So let's go in and let's learn a little bit about what I had to do to fix this thing. Okay, here is the main board on the FANUC PPR, and this is where there were a number of problems with it. I actually found a new old stock logic board on eBay and ordered it, but I'm both short on patience and I have an excess of stubbornness, and I decided I was going to fix this one even before the other one had shipped. I started diagnosing this one, and I managed to fix this one, and I want to go through the diagnostic procedure a little bit so some people know what I did and what you might look for when you have, a microprocessor-based or microcontroller-based vintage equipment that doesn't work. So the first thing you do is the first thing I do is I look at the CPU and see, is it doing instruction fetches? We can see there's an external EEPROM here. So it does interface with that, and it does pull instructions from it. You can look up the 8031 AH part number on the internet. You'll find out it does not have an internal EEPROM. It uses external. So you would expect instruction fetches. It was not fetching instruction. That, leads you to the next diagnostic step, which is you look at the reset. So every CPU will have a reset, and if something is stuck in reset, then obviously it's not going to fetch instruction. So I looked at this. I found the reset was good. Then the next thing I look at is I look at the clock. Is the chip getting a clock? If it's not getting a clock, it's not going to fetch instructions. So I found the clock was bad. And what it had in there was it had these two weird things. This one was here. This other guy was here. I looked these up on the internet. There's no data sheet for these things. There's really no indicator what they are. This one on the board was marked Xtal, like crystal. It's in a 14 print footprint, but it only had 4 pins. This one here, it didn't say what it is. There was some stuff on the internet from some people who wanted to sell them for like $500 each. Yeah, people really wanted $500 for this little thing. That this was a clock generator. So my hypothesis being that the small one here, someone took a quartz crystal and they potted it in this goo. They probably did this for vibration resistance. So what we'll do is we'll take that out and we'll check it. And then similarly, my hypothesis is that someone took the rest of the parts that make up a crystal oscillator and potted them in this goo. So 2 wires from this one package ran into there. So 2 wires from there to there, and also a hot 5-volt in the ground fed into this, and then a clock out to the CPU went into this. So my hypothesis again being that we have a crystal. And we have all of the rest of the guts, the transistor, resistor, capacitor, whatever else it takes to turn that crystal into an oscillator. Okay, so the FANUC chip is hooked up to my frequency counter in crystal measuring mode. It's got a special mode that you can stick a crystal in and it'll measure it. I couldn't actually stick it in there, so I ran a couple wires, ran it over here to the package. And it's reading 11.0591 megahertz. Now, 11.0592 is actually a very popular crystal size, so I suspect that's what it is. So I verified that hypothesis. This does resonate at 11.592 megahertz. So clearly that is something you would use as that frequency for an oscillator for an 8031 CPU. So what I did is I set about, could I make something in its place and do away with these weird, sealed up, extremely expensive custom packages. And fortunately, you can just buy an 11.592 megahertz oscillator nowadays. It's a nice 4-pin device, takes a hot ground, and has a clock out. I did make a little custom socket. It wouldn't just plug in, the footprint wasn't the same, so I kind of have a socket and a few little bodge wires running around so that I can plug it in where this thing used to be. And we'll try that out, and I expect the CPU will be clocking. So okay, at this point I was not done yet. There was clocking, and there was what looks like an instruction fetch was occurring, but the program wasn't executing properly, and the data bus just looked all screwy when it was doing that instruction fetch, like something was interfering with the data bus. Okay, so at this point I had to do a little bit of reverse engineering. So I read up a little bit on the 8031, and I did some reversing of the generator schematic from parts of this board. Found out, yeah, we have the 8031 CPU. It has a shared address data bus, so the lower 8 bits of the address are shared with 8 bits of the data. So that means it has an address latch. I found that there, 74 or 373. That made sense. Now it's got a ROM over here, and we need something that buffers that ROM, so there is a 74LS244 buffer over there, and it was connected, you know, through some additional logic to the signals on the CPU that engage this when it fetches instructions. Makes sense. Now there's also over here some output buffers and some input buffers for ports. And so there was an input for a 244 that reads from the ports. And what I found was that this one here for the ROM was turning on and off as expected. But the one over here, which is the input port for the various ports on the board, you know, to read from the tape reader or to read the status from the punch or to read the status from the key switches, that one was stuck on 100% of the time. So both this buffer and this buffer were both throwing stuff on the data bus, sometimes at odds with one another. One would put out a low, the other would put out a high, and your data bus just bounces up and down. The whole thing draws excessive current. It just flips out. Now to diagnose that, I had to reverse a whole ton of stuff on here to figure out what turns that input transceiver buffer on and off. And what I found is that there was a common pull-up running to about half a dozen chips, all kinds of gates that they wanted pulled up, which all came over here and went to a resistor, I think it may be this one here, which pulled it up to 5 volt. And when I looked at that common pull-up, which was pulling things up to 5 volt, it was at -1 volts. So it was like a hard low on that pull-up. And that pull-up was clearly supposed to be +5. You know, people will do that on gates rather than wiring something they want pulled up directly to the 5. They'll pull them all together and hook them to a resistor and pull that up to 5. Maybe that saves you a little bit of current draw. But this thing was getting yanked down to -1 volt, which was, through some logic, causing this buffer to stick on. Now, how is -1 volts going to get onto a digital TTL bus? That shouldn't happen. Look around, and some things that come out as suspicious are these two guys here. These are the serial transceivers, and these are 75-188 and 75-189. I forget which is which. One is the input transceiver, one is the output transceiver, very popular chips for the day. And the output transceiver has a plus and a -12 volt source going into it. And those, you know, are used to synthesize the RS232 signals. The input transceiver doesn't need that, but the output one does. So I desoldered both those guys, I yanked them, and all of my problems went away. The CPU booted, the lights went out on the interface, it was all golden. So I expect what happened is someone probably took the serial port, you know, this thing has a DB25 on it, someone probably took that serial interface and plugged it into something that was, you know, another DB25 that was not a serial port. And, you know, maybe it was high voltage, who knows what happened, but someone just murdered that output transceiver on the serial. And when they murdered that thing, they did it in such a way that it was bleeding that -12 volts that goes into it down into its inputs and yanking down that shared pull-up. So I socketed those guys and I replaced them with new ones, and lo and behold, the board now works most of the time. So why doesn't it work 100% of the time? Well, that gets back to the reset circuit. So the reset circuit actually came over here and hooked up here to a comparator, where it compares the 5 volt. It takes your 5 volt input signal, it runs it through a voltage divider to produce about 1.5 volts from a 5 volt input. Now, as the other side of the comparator, it takes a 1.5 volt reference signal from the power board, compares those two, and if it thinks the 5 volt signal is good, it pulls it out of reset. Thinks the 5 volt signal is too low, it leaves it in reset. And I found that maybe the components have drifted or something, but it was just way too tight on that reset circuit. And sometimes it was tripping, and it was thinking that the 5 volt wasn't good enough, even though it was, and throwing the microprocessor into reset. It'd be better just to replace this with a modern reset circuit rather than a comparator, a voltage reference, a resistor ladder, whole bunch of crap that they put into there. But I botched it here. I took part of the resistor divider that feeds that, I stuck an existing resistor on just to yank it a little bit higher, to yank the signal a little bit higher, and to just give it a little bit more room on its power good signal.
And then we finally got the thing to the point where it was 100% reliable. Now I've made a few modifications. If you look, let me flip this around. Up here, I added a reset switch. Because if you're trying to diagnose a CPU that is not clocking, is not fetching, is not coming out of reset properly, a reset switch can be a really handy thing. Otherwise you've got to power cycle it. But you know, push the reset button and it will reset the thing, and you can look on your logic analyzer and see what's going on. So indispensable, have a reset switch. It was as easy as just reversing the schematic, finding the right place to insert it. Now you do want to hook your reset to a place that has like an open collector output, because you don't want to be competing with a signal that is being positively driven with your reset switch. Most reset switches are ground, so you want to find an open collector output where something else is driving it ground, has a 5-volt pull up, you put your reset and you force the pull down. The way this worked is the 8031 has an active high reset, so they do have an inverter gate. So it just means going into the right side of that inverter gate, which if you look at the back, you can see I just ran those wires down there to the right side of that inverter gate. Now I made a couple other little changes over here on the power side. So this is where the power comes in from the 24 volt and the 5 volt. So on the 5 volt I put a transient voltage suppression diode, a TVS diode. That's 5.1 volt TBS. I do that on a lot of my vintage projects and sort of high value projects and such. That diode will have a double effect. One thing it will do is if there's a huge power spike that, you know, is the type of thing that might destroy chips, it'll shunt that out. But it'll also, if you get over voltage, you have to be over voltage by, I don't know, like 20% or so for this thing to kick in. So if you get, I don't know, up around like 6 volts maybe, this thing will start to kick in, it'll start to conduct pretty hard, and you'll blow the fuse. So this is kind of like a cheap catastrophic overvoltage protection device, as well as a transient suppressor. So just because that power supply seems a little bit funky, I threw that in. Secondarily, because that 24 volt supply was floating up to 34 volts, I'm like, I don't like that. I'd like it pulled down. And a 560 ohm resistor, I think only dissipates like 100 milliamps ish. I'll run the calculator on it later, but it dissipates a fairly low amount of current, but it was enough to kind of yank that supply down into a stable 24 volts. So I put that on there, and it gives me some confidence that the thing is not, you know, overvolting and running into a component limit, you know, like putting 34 volts into a 35 volt capacitor, and you get a little bit too close for comfort there. Pulls it down maybe about 26, 27, 28 volts into a nicer margin of safety. So it's easy to throw that on, and it dissipates a small amount of current. So those are two things I did that are not necessarily mandatory. Okay, I also did a little bit of work on the power supply board for the FANUC PPR. And first of all, let's take a look at these fuses up here. Let me try to convince people I'm not completely incompetent and explain what happened. So it's got these little tiny fuses here that go in here. These things are about $3.50 a piece. There's three 3.2 amp ones and 1.3 amp, and they're on the, I think they're on the minus 12, the plus 5, the plus 24, and the plus 17 rails. And what happened is I had a couple of accidents here. The first thing I did is I wanted to look at the voltage output on the 5 volt under load, so I hooked up my oscilloscope probe to it. I checked it twice. I was really careful. I checked it twice, but I hooked up that probe backwards, so I grounded the oscilloscope to the 5 volt outline. Kaboom goes a fuse. You have to be really careful with that. You don't want to accidentally plug your oscilloscope in backwards, because your oscilloscope may be grounded. You will ground it through the probe lead. You could blow a probe lead in half. Who knows what damage you could do. Fortunately, we only lost the 5 volt fuse. I wised up. I added the first of these. Replaced the 5 volt while I wait for these specialty. The only places you can buy these things is from like a CNC part reseller, and they're like $3.50 a piece. So I've got some on order, but it's gonna be a little while before they get here. So how did it happen 2 more times? Well, I noticed the 24 volt on this was reading a little bit hot.
It was reading about 34 volts. I was a little bit worried about that. I want to know, is it really regulating to 24 volts out, or is this just kind of floating up? As things sometimes do, just kind of float up a bit, but will get pulled down when you put a load on them. So I hooked up my my DC load to it. This time I was careful. I got the polarity correct. The DC load was registering, 0 amps. I hit the on button and kaboom goes fuse number 2, the 24 volt fuse. So what happened here is I had forgotten that my DC load will automatically default to the previous value that it was set to. Even though it might say 0 on the display, that's the actual reading, not the set reading. So when I pushed the on button, it pulled 26 amps through a 3 amp fuse, and kaboom went the fuse. So okay, I swapped the 17 volt fuse into the 24 volt fuse position, turned on my DC load, I pushed the set button, dialed it from 26 down to 0, pushed on again, and kaboom goes a third fuse. And what had happened there is I had forgotten that my DC load, you actually have to push again, you have to push set again. So you have to push set once to go into set mode, then you set your value, then you push set a second time for that value to take, and I didn't push it that second time. Okay, so 3 blown fuses needed me to put in 3 fuse holders. Once the new replacement fuses come from the specialty store, I will do away with those fuse holders, and this won't look like an amateur was in here again. So the power supply board, I found that it checked out pretty well. So there is a diagnostic procedure. What they do is they have you put a 5-watt load on the 5 volt. So I had a nice 5-watt power resistor. Hook it across the 5 volt there. You put some load on the supply, and then you go around and you do your measuring. Everything was in spec except for the 24 volt, which says it can be up to 2.4 volts over, and it was reading about 34 volts. So it's like 9 volts over, which kind of a lot. Now, it could be the manual is wrong there, and that's supposed to be 24 volts under load. Wasn't completely sure. I did start pulling some parts on this, some caps and such, and actually doing a little bit of reverse engineering. I pulled off these caps over here, these ones, and all of the caps tested good. I even pulled out these big guys here. These are 470 UF 200 volt caps for the switching supply. I pulled those out, tested them. They were fine. There was some resin on the back of these, so these had been replaced before, both of these guys. As well as there was evidence this relay here had been replaced before by a previous owner. So this board's been reworked before. All of the caps were found to be within spec. I did pull one down here, which I think was a 330 microfarad 25 volt, and he tested fine, but there was some he was this guy here, but there was some gunk around the bottom, like there had been some leakage, and I replaced him with a modern replacement. So the modern replacement, same rating, same temperature, same voltage, same microfarads. It is a much smaller cap. Things have just gotten that much better in the last 30 years. So anyway, I consider the power supply board to pretty much be fine, minus my screwing around with it here, unfortunate bodges, which we will do away with in time. And we're ready to put this back together. Okay, remember the demo we did at the beginning with the RC2014? Let's do that again with the Heathkit H8 for my Heathkit H8 fans out there. Now the nice thing about the H8 is it was designed to be used with a paper tape punch and reader. Heathkit had the H10, which you could buy, and it would punch your tapes and it would read your tapes. And very few of those seem to survive today. They're kind of hard to get. I'd love to have one. I'll settle for this for now. But the nice thing is we can use the actual software that was intended to be used on the H8. We don't have to have me go invent some kind of tape loader. It actually works. Now what I have in here is I have a board designed by Norberto Collado that is a tape interface. It's actually for the magnetic tape, but the way Norberto designed it, you can hook a serial device up to it, and it'll function just like you had the H10 hooked up to the, I believe it was the H8 2 parallel board. Works the same way using this tape board of Norberto. So we've got everything hooked up here. We've got extended Benton Harbor Basic. This is the basic that you would have loaded off of tape. I kind of cheated and loaded this by just injecting it into memory because it's like 120-foot tape or so to load this thing. And we might actually try that later. We'll see. But anyway, we've got extended Benton Harbor Basic loaded. There it is. You know, here we are. Now let's type in a short program. Now, one thing about the early Benton Harbor Basics, they did auto-completion. And they didn't even give you the option on this. It just does it, which is the most annoying thing ever. So if I hit PR, it turns into print. I mean, maybe that's fine if you're used to this. But me, I will just type print and then I end up with a PR, int, and a parentheses. It gets all messed up. So I may make a few mistakes while I'm doing this. But let's see. Scott was here. Oh, did I actually get that character stuck at the end? Maybe I did. See, there I just did it with the list. L-I-S. Okay, 10 PR was here. We'll get this right, trust me. PR, the quick brown fox jumped over the lazy dog. We do that quick, blah 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 blah. 30 for I 1 to 10. I'm just typing some basic stuff in. Let's hope I get it right. Print I. Next I. All done. Always good to have a non-trivial program. List. Okay. Looks reasonable. Does it run? Did I type it in right? RU run. Just like before, let's send this to our paper tape punch. Turn it on. Let me form feed it a little bit. We're ready to punch, so I'll put it in remote mode. I'll hit paper tape punch, and then I will do a dump. They call the save command dump, and we'll just call the program. It actually does take a program name. We'll call it Scott, and away we go. And form feed it a little bit. There's our tape program. So what we will do is we will reload Benton Harbor Basic, just so that we can prove that memory is erased and we load the tape. So let me go ahead and I'm going to reboot the computer and reload the Basic. Okay, so freshly rebooted, as expected. It's empty. Let's take our tape and read it. So I'm going to put it in the tape reader. Left myself a whole lot of room over here. There we go. And then we will do a load. You have to give it the file name. It actually does check the file name. Enter. Yeah, I'm sure. And then I'll turn on the paper tape reader. Found it. Finish loading it. And there's our program. What's RU? What? Huh. Unlock. And run. There we go. So there, this is what you would have actually done back in the day if you had a paper tape punch and reader like an H10 on your H8 computer. See, this is a pretty good way to store your programs. Okay, I'm going to try something here. So what I have, I told you I've been loading extended Benton Harbor Basic through kind of a side channel, just blasting it into memory. But I did actually, from my laptop, punch like 100 and some odd feet of Benton Harbor Basic onto this. And I'm going to try to load that image directly into the H8. Now to do that, I'm going to have to like make sure that this tape doesn't get like jammed up or something. It's like 100 feet of tape are going to go flying off of this thing all over my floor. Let's see what happens. So let's see, we've got everything reset. Here I'm going to push the load button on the H8, and we're just going to hit PTR for paper tape reader and watch this sucker load 100 feet or more. Uh-oh. Uh-oh. What happened? Here, let's, I snagged it and we ripped the tape, so, whoops. Yeah, so, we got part of the program loaded, but I caught the tape on something and ripped the tape. So, at this point, you're kind of done. But look at all this tape! Look at all this tape! Okay, we're going to try this one more time. So this time I have printed it to Mylar. Mylar is much more durable than the paper tape. We'll see if this will work. So we're going to load. I've also put it on this handy spool here. I'm going to see if I can just drag it kind of around, and then it'll naturally spool down there onto the floor. Find a screwdriver or something that I can use as a shaft. That ought to work. One more time. Load on PTR for paper tape reader. Okay. Is it done? Yay! Yay! Look over here. Benton Harbor Basic. Okay, I hope you enjoyed this video. If you have any interesting stuff you've done with vintage computers and punched paper tape, or maybe even just paper tape that you used back in the day, feel free to leave a comment. Thank you. Bye. Thank you for watching my video. Please visit my website at www.smbaker.com for more electronics projects and sandrail stuff. Bye.